The algebra students are to be logged into Zoom while they test, so they're here. Possibly there would be some interaction with them, but we're going to continue forward with stats. 6.5, central limit theorem, sampling distributions. It's related to what we've been doing in chapter 6, continuous distributions. The normal distribution is a very rich distribution, and we're going to see how that is, and we're going to see how what we've been learning about mu and sigma can be used to transition to inferential statistics. You might remember that there were two branches of statistics, descriptive and inferential. We want to be able to draw inferences. We want to be able to make predictions about populations, given what we know from sample statistics. So we're kind of going from here to here, finding probabilities for the normal distribution. We did that the other day with the steel rods problem. Now we're going to transition to sampling distributions. And I'm going to try to make that as easy a transition to understand as I can. 6.4, assessing normality, is kind of like it's preliminary to 6.5. Okay, one, I talked about that already. PDF, doc, or JPEG. Okay, so assessing normality. 6.5 guarantees us the ability to do certain things on the assumption of normality. Well, what justifies the assumption of normality? How do we know we have a normal distribution? How do we know we have a bell-shaped distribution? Well, there are some tests that can be used for that, and those are in 6.4, but we actually are not doing that in this class. Now let's look at this problem here. Let's see, this said, yeah. This is our problem from the other day, so you remember this. Now, let's remember what this was. Steel rods are manufactured with a mean length of 25 centimeters. Because of variability in the manufacturing process, the lengths of the rods are approximately normally distributed with a standard deviation of 0.07 centimeters. What proportion of rods have length less than 24.9? So you were able to figure that out by getting a z-score. Z equals x minus mu over sigma. And, you know, the X was the 24.9. The mu is the 25, and the sigma was the 0.07. You get a z-score, and then you go to probably the tech to get an area which will represent the proportion that we're after, which, by the way, is also a probability. Now, let's change the problem. And this little move here is going to transition us from 6.3 to 6.5. We're going to change the question to what proportion of means of samples, say n equals 30, of rods. Have length, well, the rest will be the same. Yeah. So the new question is, what proportion of means of samples of rods have length less than 24.9? Okay. So it's not just one rod, samples of 30 rods, and then we're looking at the means. That is the twist to this problem that will move us into 6.5, sampling distributions in the central limit theorem. Okay. Now, there is Q&A. So happy to go to any question that you might have on homework or anything else. What I'm going to do here is go to StatCrunch and use one of their applets, which I really love. I'm not sure how it looks to a student. But it says over here on mine, it looks like this, interactive applets. Sampling distributions. Okay, so it's going to get really wordy here when we start talking about sampling distributions, sampling distribution of the mean. But all of those words are necessary. It's true that sometimes in stats, there are words that are thrown in that really aren't necessary, that just tend to complicate things. That does happen, but this is not one of those times. All of those words are necessary. The sampling distribution of the sample mean, not the distribution of lengths of rods, but if you take samples, there's a sample mean because we're creating another variable. Those means of various samples of the entire population of, say, size n equals 30. There's variability there. And what can we say about that distribution? Here's how we get that distribution. Let's start with bell-shaped. And the bottom picture is going to be the one that has this is where we're going to get this distribution, this new distribution, which is derived from the old distribution. So here's a distribution, and you can see it's bell-shaped. And we're going to take samples from that distribution of size, well, I've been talking about 30, so let's go sample size is 30. Actually, let's take sample size 5. Okay, that's actually better for what I want to do. And so we're going to take samples of size 5. And then for each of those samples of size 5, we're going to get the mean. Oops. We're going to get a mean. And then that mean will be part of another distribution of means. A distribution of means. Okay, so here's the first one. Sample of size 5, and there's the mean of those. Okay. Again, sample, another sample, second one. Sample of size 5, and then there's a mean. Now, coincidentally, it fell in exactly the same place, which is very unusual. Let's get a third sample. Size 5, there's a mean. So we're going to get lots and lots of samples like that of size 5. Each time there's going to be a mean of the 5 numbers. And that new green distribution will be a sampling distribution of sample means. Yep. Have a good one, Angela. Have a good one, Juan. And stat students, you know, please speak up, interact with me, even though, you know, there are these other people here. Okay, so hopefully you're getting the rhythm of each time we take a sample of 5, that sample, there's a center to it, right? That mean that's falling down, that's in the center, in some sense, of this one's going to be on the left. A sample of some sense of the, or a mean of the sample of 5 each time. Okay. So we'll run 5 of them at a time. And then you can see the applet allows us to see what would happen if we did this 1,000 times. But we just keep getting sample, 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 mean, mean, mean. but we're creating a new distribution, that green one at the bottom. So you see how we're creating a new distribution, which is derived from the old distribution. The sampling distribution of the mean. Now, I'm getting that there's no question like on anything else on homework. So we'll transition to the ALA. It also talks about this. Let's look at this together. You have this open from when I sent it to you this morning. So we're going to be, working with this applet, the same one that I have open right now. Load the sampling distribution bell-shaped applet. It might have been another shape, but we chose bell-shaped from StatCrunch. Set the applet so the population is bell-shaped. Decide on a mean and standard deviation and take note of them here. Okay, so here's the applet, and I went there. Maybe I'll rehearse the steps for that. And what I want to do is we're going to do the ALA a little bit differently this time. We're going to just work in one room, in this main room. And, please let me know if you don't like that. I actually would like to share a recording of this if it's okay. Please let me know if you have any problem with that or with working with algebra students in this room. But I would like to work in this main room in the way we normally do. One person will share her screen, and then everyone else will use the annotation tools in the way we normally do in a breakout room. Okay. So, but we're going to use my version of the applet. You know what? That doesn't work. Let me. We're actually going to use your version of the applet. Okay, Stella. Thank you. But what I'm going to do is while before you share your screen, I'm going to share my screen and kind of talk about how to get going with the applet. So on mine, and they've changed things here, so it could have changed on yours also. So we'll see how this goes. But on mine, it looks like this. Interactive applets. Sampling distributions. So there are a lot of applets here, and most of them are really good actually, but we're choosing sampling distributions. So maybe you're doing this on your, if you are open to sharing your screen, you're following along with this, and you're opening a browser tab for StatCrunch if you have StatCrunch. So this is not everyone. So the person that shares actually ideally will be someone who has StatCrunch. Sampling distributions. So I'm scuffling this morning. I got sick at the end of last week, but feeling better now, but not all the way back. Now, when you get to this screen, sampling distributions, there's uniform, and you have these different distributions. Interesting that there's binary, but we're going to select bell-shaped according to what the ALA is going to say. And we're just interested in the mean, the sampling distribution of sample means. So just the mean. And notice at the moment that the mean is 25. This is of the original population. Just think of that as the population of the weights of steel rods. Mean 25. Hey, that's what it was in the steel rods ALA, 25 centimeters. But standard deviation, what we have right now is 5. You can reset that however you want. And then the directions after that, I think you'll be able to follow. But whoever shares her screen will, go back and forth between the ALA and the applet. Now, what you might do is split it, maybe like this, maybe smash one side over, or maybe you'll just go back and forth. And let's see, now it says obtain 1,000 samples. And then we're going to go from size n equals, right now it says 2, but we're going to go size 5, size 10, size 20, and kind of record the information as you use the applet. Okay, so this is I'm going to stop share, and now would love to have someone take on this challenge, someone with StatCrunch who can share her screen. You'll get lots of help from the rest of us. So anyone who would be willing to do that, please do.
I'll share my screen.
Fantastic.
Can you see?
Yes. Yeah. So you're already in where you put the data, but I think what you'll do is just click that where it says StatCrunch to go back to like the home. Interactive applets. Yeah. Looks the same so far.
So where do I go now?
Where it says interactive applets, back up.
Oh, right here.
Yeah. And then you can either go back and forth between the document, or maybe someone else will read to you, or maybe guide you in what to do with the applet. Someone who has the document open.
I had closed it for to share my screen, so
Well, the first thing you'll do is where it says uniform, you'll change that to bell-shaped.
and don't we need the sample size? Or no?
5 is the first one. Okay, so Rainy or Daisy. Who else is here? Marita, Jasmine. How many times does the simulation get run of sample size 5 according to the document, the ALA?
Is it 1,000 times?
1,000 times.
Yeah, that's what I was gonna say. What's 1,000?
Okay, so now you've got a result of that. And in the ALA, we're writing down. So Chloe, if you could actually reopen that document.
The ALA document?
Yeah,
Okay.
that'd be great. And then it's asking you to record some information from this result.
Okay, 1 second. Let me pause it and then.
Sure. Yeah, you can unshare and then go back and and then share again if you would like.
Thank you for sharing your screen, Chloe.
You're welcome.
Appreciate that.
Okay, I got it now. So the mean for this one is it's this one, right?
I can't actually see your screen.
Um, can you see it now?
No, it's all I see are the words Chloe Duckworth has started screen sharing without actually seeing your screen. I saw it before, but I don't see it now. So when you hit the share button, I'm not sure which application you selected to share.
Mm-hmm.
But I think if you're just sharing your screen, your whole screen, we can see all the apps. That's
Okay.
how it's supposed to work. All right.
Can you see it now?
I don't.
No.
It's still not showing.
No. Are you selecting just share the screen?
Yeah, I selected that at first
Huh.
and it didn't work. So I went back to share the stat crunch and it didn't.
Try leaving and coming back.
Okay. Well, I'll be right back.
That's the Zoom version of the old hard reset.
What test are they talking about in the chat?
Oh, they're talking about their algebra test. Yeah, it looks like there's only one left.
Yeah, I kind of freaked out for a little bit because I thought we had a test and I was like, oh my God, I didn't do the test.
Oh no. No, it's just a test. You know, I've got a class right before this, and so we're doing this Zoom proctored-ish kind of thing with where we're, you know, asking students to be logged in while they're testing. And okay, I
You
don't
can
know.
see now.
Yes.
Could you see the document as well or no?
Well, not on this screen. Can you see it on your screen?
Yeah, maybe I need to just share the whole screen again.
Yeah. So right now what we see is that, well, what we just saw was the applet, your browser.
Can you see everything now?
Now, now I see the browser, not the document, but I think that's how it is on your screen. So it looks like you're sharing your screen. Um, and you could have two windows open at once if you want to try to do that, or you could go back and forth. Looks like there's a mean of 25.0849 for the sampling distribution of the sample means of sample size 5, 1,000 samples of size 5, and a median of 25.0704 and a standard deviation of 2.3036.
So in the document, it says the mean right here. Is the mean coming from the sample size or this one right here?
Yeah, the mean is the mean of the X bars. Okay, so, right, there are two different means going on here. There's a mean for the original distribution, and then a mean, I like to call it mean of the X bars, because those, what's X bar? The sample mean, right? Sample mean. And here we're taking lots and lots and lots of samples of size 5. And those samples of size 5 have means on average 25.0849 and standard deviation 2.3036. Now, I think what you did, Chloe, was you kept the mean and standard deviation that you were given, which, as you can see, is standard deviation 5, and the mean, it's not in the screen at the moment, but 25. And then once we got this new distribution, has these stats, these sample stats, a new sample mean and a new sample standard deviation.
That's right, right?
Yes. And then the others, we're going to have to describe the shape also, as you can see. So the others maybe can be looking at that green there and thinking, how would I describe that shape?
I would say it's like bell shape.
Yes, I agree. Is there anything else that anyone would add to that about that green shape?
Wouldn't you describe the shape? Yeah, bell shape. That's what I was about.
Yeah, and yeah, I agree. And if anyone sees anything more than that, it could be used to describe it. That's welcome too.
And so I do the next one. I can go to the next one.
Yes.
Could you also say that it's maybe left skewed because there's more on the left than there is on the right, possibly? Like if you're really trying to find another answer for it.
Okay. Okay, you might put in there possibly. Um, you think it looks maybe more. I see what you're saying. Yeah. So
Yeah, I was just throwing that out there.
possibly a little bit right skewed. Is that what you said?
Yeah, sometimes I get the left and right confused. Sorry.
Yeah. Well, like you said, the data are on the left, and then we say right skewed.
This is the one for 10.
That was well done.
And the shape, it looks bell shaped to me, yeah.
Yeah, I think it's bell shaped. I think it's bell shaped looking at the graph.
Yeah, it looks bell shaped to me too. So I feel like they all have the same meaning.
Okay, um, there's, it says compare and contrast. Say how the distributions are alike, say how they're different. They certainly are alike in some ways, but they're also different in at least one important way.
Mm,
Okay, Estrella, have a good day.
The standard deviation is
decreasing. The higher the n is.
I feel like the higher the number, the lower the mean gets, and the higher the number
Yeah.
gets, the lower the standard or the higher the standard deviation gets.
Well, not so much on the mean, right? Because the mean started there and then it decreased when the sample size went up to 10. But then when the sample size went up to 20, the mean went back up toward the original mean.
Yeah, I see now.
So for the mean, what did you guys say?
Right?
About the
Whenever the mean is at 5 and 20, it's higher than it is at 10.
I would say all of them are mostly bell shaped.
Yeah, I mean, the first one could possibly be right skewed. That could be like a difference.
I don't know how to put that in a sentence, but let me see. I don't know what it's called. I know I'm not a bit in a sentence, so
The shape of
The shape of the
shape
sample
of
size 5 is possibly right skewed.
the curve, you could say the shape of the curve, which seems like a kind of normal curve, which it is.
Anything else? That's all I can figure out from the table.
I'll just point out something for everyone because in case anyone's having trouble contributing, just to help out a little bit. When it says the distribution, or it's talking about, or the sampling distribution of the sampled mean. It's talking about all of this, right? All of this these are all components of the distribution, all things that we use to analyze the entire distribution.
So you said, can you repeat that so I can type it?
It's not anything you would type probably. I'm just saying if you're trying to come up with anything in these comparisons, contrasts, analyses of the distribution, I'm just saying this is all part of what we mean by the distribution, right? The mean, the standard deviation, the shape, that's like all part of it. Now you probably want to have that data in view while you answer that question, part E there. And
I don't think it. I don't think it really plays a big role.
well, look at what you wrote before.
So whenever it was like 5, it was higher than it was at 10 and 20, but 20 is higher than 10. That's something that we all noticed.
Yeah. That's one thing. So, I mean, you had a good answer for D, pretty thorough. So you might be repeating yourself to answer when you answer E. But yeah, I guess go ahead with what you were typing.
I was just gonna say, I was basically gonna say the same thing as the second bullet.
Okay, now in all of this info, which is a good, report on what we saw. Nareda, Jasmine, Daisy, what else in there might we put down for E to answer the question, what role, if any, does sample size N play in this distribution?
Are you asking everyone or just certain people right now?
Just anyone.
Doesn't the sample size also change of how many people are randomly selected and things like that?
Didn't quite hear that, Rainey.
Doesn't I mean not it doesn't the data?
Didn't hear
It's
it.
breaking up.
Yeah, you're breaking up, Rainey. I wouldn't say the sample size. I mean,
Oh yeah, I
the
was just
sample
looking at.
size made the mean increase when it went from 10 to 20. I mean, that's true. The sample size made the mean decrease when the sample size went from 5 to 10. Well, kind of, yes, Rainey. The sample size just is the number of people or data, right? I mean, it is that. It is that. It represents that. So that's good. I mean, that's true. It shows you understand what we mean by sample size or what the sample is. Jazzy, what about standard deviation here? Narita, what about the standard deviation? You know, just thinking about that part E there. What about standard deviation?
As the sample size increases, the standard deviation decreases.
Yes. That's exactly right. And that's, you know, that's exactly what Chloe noted in part D, but it was such a good observation. It really could stand to be made again here in part E. Nice formatting.
Thank you. I feel like that's because it doesn't play a role in the shape. I feel like.
Okay. We'll just you know, keep that issue of shape in mind and then move ahead.
Is that it for part E, or is it one more thing?
Well, we'll just move ahead and keep the issue of shape in mind because that's like sounds like you're kind of questioning that.
Mm.
But yeah, let's just look at get more experience here with this and look at the next problem.
So it's a new one.
Yeah, now that link there, that really isn't our link. We're just going to go back to the applet the same way we did the first time. And follow what it says to do. Yeah. Okay, now did you follow what it says there in 2A? Set the applets so that the population is uniform.
Okay, that should be the right way.
So everybody's watching the green, not only the numbers, which is important, but the green, the shape of the distribution, how it's changing each time.
Seems like it get higher, like it starts stacking on each other more.
I wanted to share that I don't have StatCrunch, but I'm still able to access this and do it myself.
Oh, okay, that's good to know. Thank you.
I just Googled the StatCrunch and the sampling distribution and it came up.
So you're able to use it as a guest or something like that?
I believe so, because I don't have an account with them.
Wow.
I mean, I guess I'm limited on other things, but I'm able to use this.
Oh, nice.
Oh, sample size. So normal would mean like close to the regular mean.
Well, it means like approximately bell-shaped, right?
I think this one is bell shaped.
Yeah. So n equals 30. What about the other ones, Daisy? Did it look bell-shaped for n equals 2, n equals 5, n equals 10, n equals 20?
I could go back if y'all want to see them.
I think they did, but they were just further spread apart.
Yeah. This one doesn't look bell shaped to me.
Yeah, I think it's bell shaped also.
This one?
Yeah.
To 10. Do y'all think 10 is or no?
I think 10 is
I would think so. It has a shape, it's just not perfect.
Yeah. So you think so? Or you don't?
Yes.
It is a little weird looking.
There's a concept here in stats called bias and statistical bias and a biased estimator. And basically, the idea of bias is, does the statistic hit the target of what it's aiming at? Do these shapes seem to be aiming at bell-shaped? Do they want to be bell-shaped, even if it's not perfect?
I think when this one wants to be bell shaped, but it's kind of like
They look like they want to be bell-shaped, like they're kind of biased toward being bell-shaped, even if it's the shape is rough.
so. Basically, all of them were bell shaped or wanted to be.
I don't know why they are asking that question, because you
It's in the table.
yeah, exactly. You can just put C table.
How does the size of the sample affect the standard deviation?
As the sample size increases, the standard deviation decreases.
Yeah. Is this a new one or
Yeah.
okay?
So it was normal, it was bell shaped, then it was uniform, and now it's going to be skewed. So yeah, go ahead. Yeah.
This one is definitely right skewed.
Yeah. So what you put right here basically determines how the data will show.
Well, I mean, the shape can change, right? So it starts out one way, but then some things change, some things stay the same as the sample size increases. I mean, you're taking samples of size 5, size 10, lots of them, right? 1,000 randomly chosen samples of size 5, 1,000 randomly chosen samples of size 10, 20. And in some ways, some things about the distribution change, but in some ways, they stay the same.
Like this one looked like it stayed the same to me. So this question asking which one had the right skew shape?
Well, no, they're asking about normal.
Okay. So bell shape.
Yeah.
That one was when you were just
That one was bell shape, huh? And this one
yeah.
bell shape as well. This one right skew. So them two were not the only ones that was normal. Standard deviation of the sample mean. It's the same thing.
What about shape? How does the size of the sample affect the shape of the distribution? Oh, okay, they're not even asking that in G. They might ask that below. I'm sure they will. Go ahead and scroll down.
That's it. That's the last.
Oh, that's it?
Mm-hmm.
Okay, well, they should have asked that. I should ask that. Okay, now here's Emily Padalecki. Who is Emily Padalecki? That's what I always want to know. Emily, who are you?
Sorry, it's me, Rainy. Sometimes my name just changes to that.
Okay, okay. All right, but anyway, how does the size of the sample, this is H, okay? How does the size of the sample affect the shape of the distribution?
The higher the sample goes, the more uniform or bell-shaped it is.
Yeah.
Yeah.
Also, sorry, my internet's kind of bad right now, so I'm using my phone as a hotspot and I got disconnected from the Zoom call, but I'm back.
Okay, appreciate that. Appreciate the effort. Yeah, but that was well said, Rainey. The more the sample size increases, the more bell shaped. It's like a continuum, right? It wasn't just totally skewed
Mm-hmm.
for n equals 20 and n equals 30. Chloe realizes this. But
Once it reached 20, it kind of got.
yeah, it was like it started out like skewed, and then it was a little bit more toward bell shaped, then a little bit more bell shaped, and then a little bit more along a continuum until you got to 30 and it's like totally bell shaped. So fantastic. I'm going to make a few more observations, but thanks, Chloe, for sharing and going back and forth between the two windows. Great job. Let's see.
Thank you, Chloe, because I didn't want to share my screen.
You're welcome.
Okay, so now this is something that you might have seen on there. Basically, what this is saying is you can take any underlying distribution, and if you're going to get this thing called the sampling distribution of the sample means, it doesn't matter what original distribution you have. Let's see. Okay, I guess it's waiting for me to come up with my own custom, totally weird, jacked up distribution. Okay, doesn't matter what it is. As you increase the sample size. So you're taking many, many samples of whatever size. Say 1,000 samples of size 5. I mean, we played it so that there were, we ran one at a time what that looked like, sample of size 5, and then there was a mean there. And then if you do it 5 times, then, we're getting means of 5 samples of size 5. And then, this new distribution is starting to take shape, the sampling distribution of the sample means. But then when you have 1,000 times, 1,000 of these samples of size 5, of course, you can't wait and take all day, but it ends up looking like that. And it's already looking normal. Even as messed up as that original underlying distribution was. And it's going to be looking more and more normal. Let's see, size 10, how does that look? 1,000 times. That's pretty normal right there. Pretty bell-shaped. 20, 30. It's going to be totally bell-shaped. So it could be normal. It's like mind blown, right? Because it could start out normal. It could start out totally skewed, like that one we did. It could be like some messed up thing that you just make up to try to make as look as unnormal as possible. And it ends up being normal. And so this central limit theorem, we start to see why it says what it says. The central limit theorem tells us that for a population with any distribution, skewed, whatever, the distribution of the sample means approaches a normal distribution as the sample size increases. Probably that last one that we saw with when Chloe was sharing, I think it was like exponential or something. That was like the best illustration of it because we saw that continuum of wanting to be normal, getting closer to normal, but it's still skewed, and then getting to be where it was really looking normal, bell-shaped. That was probably the best example. The procedure in this section forms a foundation for estimating population parameters and hypothesis testing. And here's why. Here's the central limit theorem. So you're given this situation that we set up with this applet. Random variable X has a distribution, mean, mu, standard deviation, sigma. Simple random samples, all of size n, like 1,000 samples of size 5 are selected from the population, okay? The samples are selected so that all possible samples of the same size n have the same chance of being selected. So it could have been any sample of size 5 that was taken out of those distributions. Here are the conclusions. The distribution of sample mean X bar will, as the sample size increases, say from 5 to 10 to 20 to 30, approach a normal distribution. The mean of the sample means is the population mean mu. So Rainey, we were trying to say, well, it's going up, it's going down. It's like, it really wanted to be just the same, basically. And it was varying, of course, because you're taking different samples. But basically the mean of the sampling distribution of sample means is the same as the mean of the underlying distribution. We might say mu of the X bars equals mu of the population. But here's the big takeaway, okay? Don't, go to sleep now, because here's the big thing. What about the standard deviation of the X bars? Is it the same as of the underlying distribution? No, it's less. This standard deviation is less. And we saw that every time. As we went across in those tables, that sample standard deviation was decreasing each time. And that's decreasing is what happens when you divide by a number greater than 1, right? The overall ratio gets smaller. And specifically, how much smaller does it get? Well, you have to divide that original standard deviation by the square root of the sample size. And that cuts down, that's why those bell shapes were skinnier, okay? Because the standard deviation was smaller, because really what they were the original standard deviation divided by square root of 5, divided by square root of 30, much less of a standard deviation, because it's a standard deviation of X bars. And we are actually going to use this in getting new stats on, what if we took a sample of size 30 of steel rods, okay? And then this sigma over root n, we're also going to use for estimation when we get confidence intervals and do hypothesis testing. Appreciate your patience. A couple minutes over today, but y'all were fantastic and a great effort today. And be in touch, and we'll see you Wednesday.
Have a good day. Be safe.
You too.